Hello mathematician, we're now going to have a look at getting the equation for the tangents and normals using the Cartesian approach. So this is our more regular approach, but as we'll see, it's not as easy as the parametric approach. So here we've got our parabola with a point, let's say call it a point P again, coordinates x1 and y1. The equation of the parabola is this. And we're going to get an expression for the slope of the parabola at this point, which will be the slope of the tangent at that point. So first of all, we take our equation for the parabola, make y the subject, so y equals x squared on 4a, and do our usual differentiation. So dy dx is then 2x on 4a, which becomes x on 2a. So the gradient of the tangent then at point P is our particular value of x, which is x1, and we place that into our expression for x, and it gives us x1 on 2a. So then, as before, the equation of the straight line is y minus y1 equals m outside of x1, so nothing new here. When we do the algebra, and the algebra is a little bit more intense when you're doing it for the general expressions here, then we get to this as our expression for the equation of the, I don't know why my pen is not working, for the equation of the tangent, parabola, in Cartesian form. I'll try again. So what we need to do is to know the steps to go from here to here. We won't often have to do it in an abstract fashion like this. We'll have particular points that we're working with, but we should know the process. So here are the steps in our algebra. Nothing unusual here. We would, as per usual, multiply through by 2a, so that gives us this line. We gather terms together, so making x1x the subject, if I take this x1 squared over to the other side, that takes me to this line. Now the trick, if you like, is recognizing that x1 squared equals 4ay1, because that's our equation of the parabola. So we've got 4ay1 plus 2ay minus 2ay1. We come to that, take 2a out as the common factor, and we've got our expression for the Cartesian form of the tangent just here. Now in a similar fashion, the gradient of the normal at P is minus the reciprocal, so minus 2a on x1. So the Cartesian equation of the normal is plug it into y minus y1, etc. And then, using similar techniques to up above, we eventually get to this. I'm not going to do this part for you. It is in the textbook, as is this part. But you should have a little go at doing this. Just be careful. Multiply through by x1 both sides, expand the brackets out. Be alert to the connection between x1 squareds and 4ay1s, and gather like terms. So convince yourself that you can do it. However, the point as always is that it's the method. And the method was pretty basic. It was just the algebra was difficult, and in fact much more difficult than in the parametric approach. So let's have a look at a question. So first part of this question says, show that the endpoints of the latus rectum on this parabola are A and B, just here. So we need to know stuff before we can go any further with this. So we've got to remember that x squared equals 4ay is this parabola. We've got to remember that the latus rectum is a chord through the focus, which will be the point 0a, parallel to the x-axis, so that makes it the line y equals a. So what we really want is the intersection of the parabola, x squared equals 4ay, and the line y equals a. So if we substitute that value of a into here, we've got x squared equals 4a squared. So clearly x is going to equal plus or minus 2a. And that's this and this. And our y value is a altogether. So again, not in any way difficult, but it's not the sort of thing that you try to commit to memory. You just say, what do I know? How can I apply it? And away you go. Part B says find the equations of the tangents and normals at these endpoints. So we've got to find the equation of the tangent here, and the tangent here, and the normals, and then we can see in part C, show that they form a square and find its area. So let's just concentrate on finding the equation of the tangents and the normals. So how do we do that? Well, again, remember our process. So what's the slope of the tangent anywhere? We saw that m anywhere is going to be, if we make y the subject, y is x squared on 4a, so that will differentiate to be 2x on 4a, so the slope anywhere on our parabola is x on 2a. So at point A, which is minus 2aa, then what have we got? We've got that the slope is x, which is minus 2a on 2a. So the slope is minus 1. So the slope of this particular tangent is minus 1, the one that passes through here. So this is point A, this is point B. If the slope is minus 1, then y minus y1, so this point here, point A, was minus 2aa, so it's y minus a equals m outside of x minus 2a, so we've got that. So y equals minus x minus 2a and then plus a, so minus x minus a. Okay, now that's a whole lot simpler than the algebraic process we went through a moment ago. So this is the equation of the tangent at A. The equation of the tangent at B will be a similar sort of thing. B is the point 2aa. So that's going to give us that m equals 2a on 2a. So the gradient is 1. It fits with our diagram. So keep checking back to your diagram. So the gradient is 1. Therefore, y minus y1 equals m, which is 1 outside of x minus x1. So we're going to get that y is x minus a. Now, what does that tell you when you think about these lines? It tells you that this line cuts the y-axis at minus a. This line cuts the y-axis at minus a. So both of these lines pass through that point 0 minus a, which for what it's worth happens to be the directrix. That fits because we know that the latus rectum is a focal chord, and we saw earlier that the tangents intersect on the directrix. But this time, not only intersect on the directrix, but also intersect on the axis of symmetry. So we keep just building little bits of our knowledge about this whole setup. Now, if we then get the normals at these endpoints, so for the normals, so at A, the slope of the tangent was minus 1, so the slope of the normal is minus 1, so that slope will be plus 1. When we put the slope of plus 1 into this equation here, we'll get y minus y1 equals m outside of x minus x1, so this. So y equals x plus 3a. So we've got a line passing through here, which is going to have a slope of 1, and it's going to cut up here at 3a, if I could get my pen to work. And at b, we've got, which is the point 2a, we've got y minus y1 equals m. Now m of the tangent at b was 1, so m of the normal will be minus 1, so that's minus 1 outside of x minus, and it's 2a, so y equals minus x, and I've got plus 2a, and bring this over, so it's plus 3a. So again, we've got two lines which are perpendicular to each other, and they intersect at 3a. So when we look at although it doesn't look much like it here, to show that these tangents and normals form a square and find its area, we've got that this line is, and I should be writing this down, but I'll put it up here and you can go through the process of writing it down. So this line and this line are parallel to each other, they have the same gradient. These ones are parallel to each other, they have the same gradient, so we've got a parallelogram. These are right angles because they're perpendicular. So with those right angles, we've gone from having a parallelogram to a rectangle. Now if we think about we could go through and use the distance formula to get the sides of this and compare them, but if we think about the distance from here to here, that's going to be 4a, because we're going from minus 2a to 2a. This here is going to go a distance of 4a, because we're going from 3a down to minus a. So if we have a rectangle which has diagonals of equal length, 4a, they will intersect each other and they'll pass through this point here. They're all the conditions we need to show that this is a square. And if it's a square, to find its area, well, to find the area, we could go back into autopilot mode and say the area of a square is the side length squared, and we could use the distance formula to get the length of a side. Now, that wouldn't be at all difficult, and then we could square that. Or if we just keep thinking about things, we could see that this square is really two triangles. Those two triangles on a proper diagram would be identical, and the area of one of those triangles will be a half of its base. So there to there is 4a times its height. So from there to there, from a to minus a is 2a, and we've got two of those triangles. So we can see that when we're finished, that becomes just 8a squared. A whole lot easier than using the distance formula, but I guess even that's not too bad. So again, think about what it is that you need to understand and what you should be committing to memory, and then have a go at 9G.